In a previous video we looked at simple indexing, and the formula for simple indexing is 40 over n, because the dividing head takes 40 turns to make one complete revolution. So if, for example, we needed to cut 30 equal pieces of geometry around a diameter, it would be 40 divided by 30, which would be 4 over 3. If we multiplied it by 22, that would give us the 66 whole plate that we have on the dividing head for the denominator. We need to multiply the numerator by the same number, or, in other words, 88 over 66, which would equal one complete revolution and 22 spaces on a 66 whole plate. If we have a look at 67 divisions being required to be cut around a diameter, example 67 equally spaced holes around a diameter, and we tried to use that simple indexing formula 40 over n, it would work out to 40 over 67. The 67 will not reduce, and the problem is we do not have a 67 whole plate on the indexing head. With our dividing head, we know that if we turn the index crank, it will turn the spindle. And this gives us that 40-to-1 ratio. In other words, one turn of the crank causes the spindle to turn 1/40th of a turn. So 40 turns of the crank would cause the spindle to turn one complete revolution. If we put a gear on the back of the spindle and we turn the index crank, the spindle turns, causing this gear to turn. It in turn will cause the gear in the train to turn, causing it to come back inside the dividing head, which is a sleeve that is sitting over the crank, and it causes the whole plate to turn. Now we need to make sure that the whole plate is unlocked in order for that to happen. So in other words, when we turn the index crank, the whole plate will either advance or retard along with the index crank. So the whole plate will turn, thinking that it has more holes than it actually has. Because we can't use 67 divisions with simple indexing, we're going to use differential indexing. And we know we need 67 divisions, but we're actually going to lie to the dividing head and tell it we're going to use 70 divisions. And what's going to happen is we're going to create an error, and then we're going to correct the error. So the formula for differential indexing is a minus n times 40 over a. We're going to have a look at the last part here, which is the 40 over a, to get the indexing. So 40 over a, or 40 over 70, which is the incorrect number, gives us a ratio of 4 over 7. Now if we find a multiple that will give us the denominator of the whole plate we require, in this case we're going to use 21 whole plate. So 3 times 7 is 21, and again we have to do the same thing to the numerator. So 3 times 4 is actually 12 spaces on that 21 whole plate. And again, this is incorrect. So what we're going to do is turn the whole plate, or rotate the whole plate underneath the crank pin, in order to correct for this error we're doing, because we do not have a 67 division whole plate and we couldn't reduce it. So the second part is we're going to take the whole formula and we're going to create a gear train to drive the whole plate, causing it to rotate. So if we use a minus n times 40 over a and we plug it in, it is 70, which is our approximate, over our actual number we require, which is 67, times 40 over 70, which is the indexing we created, 40 over a. So 70 minus 67 will reduce down to 3 times 4 over 7, which is the simplified fraction. Should give us a fraction of 12 over 7. This is our gear train ratio. So now what we're going to do is take that 12 over 7, or our gear train ratio, and we're going to multiply it by something in order to give us a ratio of gears that we may have. And if we multiply it by 4, so 4 times 12 gives us a 48, and 4 times 7 gives us a 28. And if you have a look in your set of change gears, you should have a 48-tooth change gear, and you also should have a 28-tooth change gear. Now what we're going to do is we're going to put the 48-tooth gear on the spindle, in other words, coming out the back of the dividing head, and that will become the driver. And then we'll put the 28-tooth gear going back into the worm shaft, which is going to cause that hole plate to turn underneath the crank pin. So here's a demonstration dividing head I've set up to show the formula we calculated. And we have a traditional dividing head where we have the crank pin that turns over the hole plate, meshes with a worm and a worm gear inside it, creating a 40-to-1 ratio. So 40 turns of the crank will turn the spindle one complete revolution. That's that 40-to-1. In this case here, what we've done is we have put a shaft in the back of the spindle and have put a gear to it, and I'll give you a better view of this in a minute. And we have power coming out of the spindle into the gear, through a gear train, back into another gear, and into the dividing head. This will cause the hole plate to turn. Also, too, this has a great big long casting on it, so we could mount it to a milling machine and allow it to be drove off of the milling machine feed on the table. So here's that gear train setup that we calculated. We have the gear coming off of the spindle, which is our driver, and we have an idler in the middle, and then it goes into a driven. Now, if you remember the fraction, it was 12 over 7, and we multiplied it by 4. So 4 times 12 is 48. So there's our 48-tooth gear. 7 times 4 is 28, so there's our 28-tooth gear, and we have an idler in the middle. Because the fraction was positive, if we have one idler, we have this gear going clockwise, the idler will go counterclockwise, and then the driven will go clockwise. So in other words, these two gears, the driver and driven, are in the same rotation. What this does is this causes the index crank and the hole plate to rotate in the same direction. Had the fraction been negative, we would have put another idler in, so it would have went clockwise, counterclockwise, clockwise, counterclockwise. So in other words, driver and driven would be in opposite rotation, which would cause the hole plate to turn in an opposite rotation of the index crank. So I'm just going to turn the index crank, and you will be able to see that we have the power coming out the back of the spindle, turning the gear. The idler is turning from the driver, and then it turns the driven gear. And again, we have that 12-to-7 ratio, driver-driven. This is known as a simple gear train because we have one driver and one driven. Sometimes the fraction, that 12-to-7, will not work well. Example, let's say 4-to-1. So the smallest gear we have is a 24-tooth gear, so 1 times 24. But 4 times 24 would be 96, so we don't have a 96-tooth gear. So what we would have to do is compound gear it. So we would have two fractions, 2 over 1 times 2 over 1, which would give us that 4 over 1. And we would have one ratio of gears going here, and then we would put a second gear right on top and having it mesh with the driven. So we would have one ratio here, 1 to 2 here, and a second 1 to 2 here with a second gear on top. That would be a compound gear train. Again, what you're seeing here is a simple gear train. One driver, one driven. I've now moved the camera around to the back of the hole plate on the dividing head so you can see the locking mechanism for the hole plate. And that's it here. It'll look different on other dividing heads. But what happens is if this pin is engaged in the back of the hole plate will not turn, which is what you want for simple indexing. Because we have power coming back into the dividing head, we need this hole plate to turn. So we need to make sure that the pin is disengaged, allowing the hole plate to turn. Okay, we're now around to the front of the hole plate with the crank in front of it, and I have it set up so the pin is engaged with the 21 hole plate. Again, we never ever count the hole we're in, so we'll count the spaces between it. So 1, 2, so on and so forth. And the sector arms are set for 12. So one sector arm will go here, and then it will come around and touch this sector arm. Before I use any dividing head, I always want to give it a couple of revolutions, and I always like to go clockwise. So I'm just going to start to spin this, and you can see that whole plate is turning. That is caused by the power in the gear coming back into it. So I'm just going to drop the pin in, set the sector arm, and then what we would do is we would cut a hole on some material that's being held in the spindle. And once that's done, then we'll pull the pin out and we'll just index it around, drop the pin before I get to the sector arm, let it fall in, and then take the sector arm that is going to push up against the pin, and now I'm ready to cut the second hole. If required, I would do this, in this case, 67 times, and the spindle would make one complete revolution. I'm just going to zoom out so you can see the whole thing working, and that's it.